Hello, welcome to another practice problem. This is 10.17 from the text. It shows here a beam with a loading, and we're asked to use the double integration method to determine the equation of the elastic curve for the cantilever beam, the deflection at B, the deflection at the free end, the slope at the free end, and we need to assume the modulus of elasticity and moment of inertia are constant for the entire beam. So the first thing that we should do is just the same thing that we have done for all problems thus far, is finding the reaction at the fixed joint. So I've already done that and drew a free body diagram and determined what our moment is and what our reaction in the y direction is. So the next thing, we'll draw a quick free body diagram here with an arbitrary cut distance of x and a new moment, and so then what we can do is we can build a moment equation from the distance between, and this is going to be valid from A to B, okay? Or our distance when x is from 0 to L over 2, okay? So what this will be is just summing the moments about, say, our shear point here, and sum our moments about V equals 0, positive direction going convention. We'll say moment at V minus moment at A minus the reaction at A multiplied to X equals 0. And so this will then become our moment V will equal our negative 3WL squared over 8 minus WL over 2 multiplied to X. Okay. Oops, I'm sorry. This is a plus. Okay. So now what this is our moment that we determined. What we can do now is using our double integration method, we can say modulus of elasticity, moment of inertia, and the second derivative of our deflection with respect to x equals the moment of x, which was what we just determined was negative 3WL squared over 8 plus WLX over 2. And so we can integrate this equation and get EI d nu, this is nu, not V, don't confuse that with shear, that is our deflection. I'm using convention here for the textbook. And this will be integrating this, we'll just multiply this to x, it becomes 3WL squared x over 8 plus WLX squared over 2 times 2 is 4. So 4, and then we'll have a constant of integration. We're going to call that C sub 1. And then to get to the deflection, so this is our slope equation, right? And so the next one, what we'll do is, so I'm going to write slope here. So the next one's going to be for deflection. And so that's EI nu equals negative 3 WL squared x squared over 16 plus WL x cubed over 12 plus our constant of integration multiplied to x plus another constant of integration. Okay, so now we have these two equations, and the next thing that we can do is know that our boundary conditions, right? Going back to our diagram here, we can say, or better yet, let's go up to the original diagram. So since we have our fixed connection here, we can say when x equals 0, our slope, right? So the derivative of deflection with respect to x will also equal 0. and we can say our deflection equals 0. Okay? And these are going to be the boundary conditions to be able to help us figure out what our constants of integration are. So using that, we can just plug for our slope. We can say 0 equals negative 3w squared multiplied to 0 divided by 8 plus WL0 squared divided by 4 plus C sub 1, and then we can determine that C sub 1 equals 0. And for deflection, we can then plug 0 in for this as well, because we already determined 0 equals negative 3WL squared multiplied to 0 squared divided by 16 plus WL multiplied to 0 cubed divided by 12 plus C sub 1 multiplied to 0, which is also 0, plus C sub 2. And then we determine here that C sub 2 is also 0. Okay, so now that we know this, we can then substitute the values in, or we can find what our deflection is at B, which is the next, which was part B, I guess, of this problem, right? Yes, part B of this problem. So find deflection at B. So let me zoom out here. And our actual equations, right? Our equations for 0, between 0 and L over 2, our slope then equals EI d nu over dx equals negative 3w L squared x over 8 plus WLX squared over 4. Okay? So the deflection at B, what we'll do is we'll just take our value of the x, which is L over 2, and plug it in anywhere we see an x. And so we'll just go ahead and say EI dB over, or d nu over dx equals negative 3w L squared multiplied to L over 2 divided by 8 plus WL multiplied to L over 2 squared divided by 4. And so you should be able to solve this and find what the deflection is. You'll get... Okay, so reducing this, you should be able to reduce this down, and I'm not going to go through the math because this is really just algebra at this point, no longer mechanics and materials. But you could say EI d nu over dx then equals our negative WL cubed over 8. And then we could say our slope at B, so at B, our slope equals negative WL cubed over 8 EI. Okay? So that's the answer for part B. So part C, what we're going to do now is build our equations. So I'm going to draw another free body diagram. Going from A to some arbitrary distance past L over 2, okay? So if this is where B is, right, this distance here is going to be L over 2, then this distance here is going to be X, then this distance here is going to be X minus L over 2, okay? And then our distributive load is going to be here, right? And this will be W, and we have our moment here, V, and this is our shear, our reaction, AY, and then our moment at A. Okay? So, since I drew this right here, we can then solve for our moment, M sub V. And so summing our moments about the shear point equals 0, positive in the convention. And then we'll say our, looking at our value here, we'll have m sub v minus ma minus reaction ay multiplied to x plus our distributive load, which is going to be w, multiplied to the distance, which is going to be x minus L over 2, and then multiplied to half of the distance, because we'll condense this to a point load, so it'll be x minus L over 2 divided by 2, and then all of this equals 0. So then we can reduce this down and say that the moment at B equals, or the moment at x distance away, which is the moment at the shear where we're making our shear cut, is then going to equal our negative, just reducing a couple things here, so negative x minus L over 2 quantity squared plus WL over 2 multiplied to x, and then minus 3WL squared over 8. And then we can reduce this further and actually say our moment then equals negative WX squared over 2 plus WLX minus WL squared over 2. Okay? And in the same process that we've done before, right, in the previous parts of this problem, we're going to go ahead and integrate this twice. So we can say our EI d nu squared, or second derivative of, sorry, not squared, equals our moment at x, which now equals negative WX squared over 2 plus WLX minus WL squared over 2. And then integrating this, we get EI, and this is our slope equation, which is going to equal, integrating this, we get negative WX cubed over 6 plus WLX squared over 2 minus WL squared over 2 multiplied to x. Okay? But we need to add our constant of integration. So we're going to, this is our third constant, so we're going to call it just c sub 3. Okay? And this is our slope equation. And then we'll do our deflection equation here. So deflection. And so EI nu equals, integrating our slope equation, we get negative WX to the 4th over 24 plus WL x cubed over 6 minus, what is that, WL cubed, nope, WL squared x squared over 4 plus our third constant of integration multiplied to x plus a fourth constant of integration. And the reason why I'm adding this is c sub 3 and this is c sub 4 is because we need to make sure that these are different constants of integration from the previous two that we've already determined, okay? And that's important. So what we need to do now is determine what these constants of integration are for both our deflection equation and our slope equation. So if we recall what we solved in part B, we know that the slope at B is going to be negative WL cubed over 8 EI. So I'm going to write that down here, right? So slope at B equals negative WL cubed over 8 EI, okay? So using this, right, we know at B, that means when x equals, right, when x equals L over 2, because going back to our original, or not our original, but this, this diagram here that we drew for part C, right? When x equals L over 2, then our deflection is going to equal a value here, right? And our slope is going to equal a value. So we can determine what those are. So right now we're doing our slope. So what we'll do is go ahead and solve for this. EI d nu over dx equals negative w when x is L over 2, so we're going to multiply or plug that in. L over 2 quantity cubed over 6 plus WL L over 2 quantity squared over 2 minus WL squared over 2 multiplied to L over 2 plus C sub 3. And remember, all of this equals our negative WL cubed over 8 EI, right? So using that and condensing this down, what we should be able to reduce, I'm not going to do the algebra for you, but you should be able to get to the value that equals, we'll say C sub 3 is WL cubed over 48, okay? And that's C sub 3. So now we need to do this same thing for deflection, okay? So I'm going to take the C sub 3 value and plug it into this equation here so we can actually solve. So EI nu equals negative WX to the 4th over 24 plus WL x cubed over 6 minus WL squared x squared over 4 plus WL cubed over 48 multiplied to x plus C sub 4. So now the question is, when we use our boundary condition, which is going to be at point B, so when x equals L over 2, what does nu equal? Okay? So what we can do is go back to what we solved for in part A. So let me zoom out here and go back to our original equations that we were deriving. We can go to our deflection equation, right? And our deflection equation that we had here, this one right here, this deflection equation, because we determined C sub 1 and C sub 2 are both 0, so we can say our deflection EI nu equals negative 3 WL squared x squared over 16 plus WLX cubed over 12. And then we can determine what the value is, right? What is our deflection at L over 2? So we can just plug L over 2 in for x and solve for our deflection, and you should get deflection equals, I wrote it down, so hold on. Okay, so our deflection equals negative 7 W L to the 4th over 192 EI, okay? And that's at B, right? So using that, we can come back over here to our other equation, what we're solving for, and we can say, well, we know at L over 2, this is what our deflection is, so we can just plug that value in and say negative 7W L to the 4th over 192 EI equals negative W multiplied to L over 2 to the 4th divided by 24 plus WL L over 2 cubed over 6 minus L WL squared multiplied to L over 2 quantity squared divided by 4 plus WL cubed multiplied to L over 2 divided by 48 plus C sub 4. So this is a pretty big mess right here, solving this equation. If you do all the algebra and solve this, you should get C sub 4 then equals negative WL to the 4th divided by 384. Okay? So that's C sub 4. So now we solve for c sub 4 and c sub 3, right? So we can rewrite our equations, okay? And say our deflection equation, which is what we're looking for, because I think, let me go back. All this work, sometimes we forget what we're looking for. So the equation for the elastic curve for the cantilever beam, okay, I think we've already done that. Deflection at the free end and slope at the free end. So we're looking for deflection at the free end and slope at the free end, okay? So now what we can do is say our deflection equation, knowing these two constants of integration, our deflection is going to be EI nu equals negative WX to the fourth all over 24 plus WL x cubed over 6 minus WL squared x squared over 4 minus WL cubed multiplied to x divided by 48 and minus WL to the fourth over 384. Okay? And so this is the equation for L over 2 is less than or equal to x, which is less than or equal to L. Okay? This is what this equation is valid for. So then what we can do is just plug in. So we should just plug L in for anywhere you see an x in for this equation, and you should get your deflection at C. So nu equals, and I'm not going to go through the algebra, but if you just plug L in anywhere you see it, it should be W multiplied to L to the fourth over 24 plus WL multiplied to L cubed over 6 minus WL squared multiplied to L squared over 4 minus W, it doesn't look right, WL cubed multiplied to L divided by 48 minus WL to the fourth over 384. That's an 8. Let me fix it. 384. Okay, and then reducing everything down, this should then equal, we get nu, or our deflection at the end of the beam, the free end, should then be negative 41 WL to the fourth over 384 EI. Okay? So then we're going to do the same thing, but for slope. So what was our slope equation at this, at the free end? Which was this equation here is our slope equation, right? We already determined what C sub 3 was. So let's go ahead and solve for that. Then we can say doing the same process that we did for our deflection at the free end. We can say EI d nu over dx then equals negative 8w multiplied to L cubed divided by 48 plus 24 WL multiplied to L quantity squared over 48, and then minus 24 WL squared multiplied to L, again divided by 48, plus WL cubed over 48. Okay, and then this should reduce down to, we'll say d nu over dx, which really equals our slope, which is theta at point C, is going to equal negative 7w L cubed over 48 EI. Okay, so to summarize really quick, we solved for our deflection at point B, right? So our deflection at point B, right, if you go back and watch the video again, our deflection at point B was negative 7w L to the fourth over 192 EI. Our deflection at point C then is negative 41 WL to the fourth over 384 EI. And our slope at C, we just solved for, was negative 7W L cubed over 48 EI. Okay, and these are the answers.